Yeah, hi. Thanks very much for that introduction, Jared. Yes, yeah, I'm the technical director here at gTET, and yeah, so we're going to talk about using geothermal heat for industrial purposes. Exactly the project that Ashley was pulled up there on his second last slide, the Smart Geothermal Industrial Loop, there down at Terralgan, and some of the work that we supported Melbourne University in undertaking. Yeah, with Christian actually. So. Yeah. Okay, so before I get into those details, just a bit of a talk about the general principles. Using a geothermal resource and say variable renewable energies, we can take that resource and pump the heat up to 120 degrees, no problem, as you mentioned. And actually now, as Jared was talking about earlier, with a better higher temperature heat pumps that are available, we can go to 150 degrees saturated steam. Yeah, so once we've got it up at that temperature for industrial use, we'll generally store the heat because the industrial use is a bit variable. Okay, yeah, so I'm assuming everybody who's watching this knows how a heat pump works, but just specifically in this case, we're taking the water and putting it into the evaporator. That makes it much better than an air source heat pump because the approach of the heat exchange is much closer, so it's much better. And you can lift it up much higher. One of the other things is generally industrial processes use a small delta T on the hot side, maybe only 5 degrees. For that reason, we generally prefer to use low GWP HFO refrigerants. They work well there. The CO2s of this world are really, really good at lifting, say, an ambient water supply up and making it quite warm. But if you're dealing in a 120 or 100 degree space, then those refrigerants seem to work better. Yeah, so that's, you may see that image in the top right look fairly familiar given a previous presentation. Yeah, so this particular project that we're supporting on, they determined that they'd have a 60 degree geothermal resource at this location from about a 600 metre depth. There's a whole bunch of modelling done on different options, different consumers and so forth by Princess. And yeah, we supported in terms of what the takeoff flow should be, heat exchanger selection, heat pump sizing, efficiency, cost. We come up with a generalised piece of equipment to go into each site so that the interface to the loop was the same with similar control system and so forth. And plus, of course, also just general industry-based thermodynamic support, like what was practical in the industry environment. Okay, so the results, just one slide on the results from this project. There was two basic concepts. One was the direct single pipe and the other one was the indirect double pipe. The indirect double pipe is like your traditional ring main type system. And the direct single pipe, because you have to re-inject it, there's you want to transport the water to another location if possible, rather than doing angled drilling and all that sort of stuff. Not my area of expertise, but anyway, so I was a bit skeptical, to be honest, about the direct single pipe because, of course, consumers are not re-injecting, but returning the cooler water back to the main heat pipe. So the downstream consumers have to add more heat to boost their system. But as you can see on the top right, yes, the parallel indirect loop traditional ring main system is slightly more efficient. So the y-axis there is a bit difficult to read, but that's basically the amount of energy you've got to put in to deliver the heating needs. So we're assuming the heating needs are constant and how much do we have to spend to get there. And but you can see, yes, it is better, but maybe not worth the capital cost of running, duplicate plumbing all everywhere and all the additional resources. And especially if you look at the bottom chart, when you compare it with the traditional equivalent, which is the gas system, whereby there was a total saving of about 20 gigawatt hours of energy required to deliver the heat to the consumers. So in this model, there was three 3 sites using the heat pump and 2 sites using just direct geothermal resource. Yep. So one of the things mentioned was industrial users typically have quite a lumpy usage of heat. Most lumpy would be, say, food processing, where they use maybe 80% of their heat in a couple of hours doing their clean in place type applications. And so they'll need some degree of storage. So clean in place would typically just use a stratified water tank to do that. For other industrial processes, it may be more appropriate to use a PCM material, especially where the storage space is an issue. So PCMs can deliver a megawatt thermal out of a 7 metre cubed volume, which is quite efficient. So those solutions also go well into the industrial space there. Yeah, just a general talk about COP, and Jared was talking about this earlier. The source temperature has a massive impact on the COP of your heat pumps. Now, it's just a general plot. It's not specific to this project, but as you can see, you know, if your source temperature is up high, you're already in a good range. And with those heating loads in winter, air source heat pumps, you may be down at that 10-degree line, really struggling. So that increases your plant size to deliver the heating that you require and increases your energy consumption. So using the geothermal resource improves your payback by reducing your capital cost up above ground and reducing your energy consumption. Yeah, so that's basically a quick 5-minute overview of the heat pump of the gTET involvement in this project and heat pumps in general.